Thank you. So this work is done in collaboration with Jim Head. This morning, Jim made an overview of magmatic processes on the moon and showed a number of examples of volcanic features that are produced by magmatic processes. He will show you more examples of this afternoon. I will speak about the largest volcanic features on the moon, volcanic plains, known as Mare, dark patches on the moon, mostly on the near side. You know them just looking on at the moon in the sky. They are known to be volcanic features, so they are known to be formed by effusive volcanism. Usually we don't see individual lava flows that form lunar mare. We do see them in some places, like this nice photo shows. But usually we don't see them because they are old, they are covered with a thick layer of regolith. Regolith smoothes everything and it is not easy to see individual lodes. Note that these nice flows are seen in an image taken at very low sun. So this is the way, one of possible ways to see these morphologies. You need to look at them near the terminator where the sun is very low. However, imaging at low sun is not easy. It has some shortcomings. First, there are very long shadows at the image. They can obscure some terrain, so you don't have access to every place on the moon. Then, because obliquity of the moon is very low, low sun shines either from the west or from the east. So only two direct illumination directions. So you have no much flexibility tuning your illumination conditions. Then look here. This is not very large place on the moon. It's a small part of Mare Imbrium. And here everything is in shadow. You see nothing. Here sun is already too high and you don't see lava flows well enough. So you have access to small portion of lunar surface in one image. And then you need to plan observations carefully, mosaic images and so on. So observations at very low sun are difficult. This is why we see these morphologies only in a few places where they are best seen. So we figured out that it is possible to study such morphologies using LoLa topographic data. With LoLa topographic data, we don't have illumination problem. It is topographic data from laser ranging, and we can illuminate it artificially any way we want. And we succeeded with this, and we see much more individual lava flows that were seen previously. If you take typical usual topographic map produced from LoLa data, you will not see lava flows. So here you see large-scale variations of topography in color shades. You see steep slopes, short steep slopes as artificial illuminated topography, steep craters, but you don't see gently sloping, low amplitude topographic features. You don't see lava flows here. We need some tricks to see them. They are in topographic data. And there are several ways to present topographic data in the way you can see individual Mare flows. We use the trended topography maps. So the idea is like a high-pass filter. We take topography and we subtract the trended surface from this topography. How we calculate the trended surface, our know-how for this is to use the median of topography in a sliding window. So typical or standard, if you want, high-pass filter is the same thing when you took the mean topography, the mean elevation in sliding window. And the results with standard high-pass filter is much worse. You see too many artifacts. So this detrending procedure, it preserves features that are smaller than sliding window. It completely removes topography significantly larger than the window. It distorts topography, heavily distorts topography with spatial scale comparable to the window sets. So any detrending procedure is doing this. Advantage of our median filtering is that this distortion is not that harmful for detection of gentle surface features. This shows example how it works. So this is artificial topography, artificially illuminated domes. And this is what you have for linear filtering, for our median filtering. So you see these domes as bright patches, bright meaning high elevation, relatively high elevation. Our approach to the trending has some disadvantage. So distortions are more complicated and counterintuitive. Or they are weaker, or they are less harmful when we try to see features. But it is more difficult to figure out what's going on when you look at features with typical size similar to special to the size of the window. So let's look at two examples on the moon. One is in the center of Mare-Imbrium here, and so this is what we see on the detrended topography map. So look at this, from white to black is plus minus 10 meters. So typical elevation differences that you see here, they are about 3-4 meters. We clearly see these large lobes. They are lava flows that form part of Mare-Imbrium surface. These particular lobes have been seen from low sun images. The image you saw on the first slides is somewhere here. And these lobes, they also were imaged at low sun and described in literature. These small lobes here, it is also texture of lava flows forming Mare-Imbrium. It was not seen before we looked at this topography. So I don't know any low sun image where you can see this pattern. Well, and we clearly see difference between lava flows of these huge lobes and these dendritic systems of very gentle ridges. They are morphologically different. So what does it mean? The way to produce single lobes, it is volume-limited lava flows, as Jim described this morning. When you have individual eruption, you start producing lava flow, and then if your source is shut off, what remains is one single lobe. To produce huge lobes, you need huge effusion rate. To produce small lobes, you need small effusion rate and short duration of eruption. If you have longer eruption or lower effusion rate, you produce cooling limited flow. So first you produce the same lobe, but then if the lobe is long enough, cooling is sufficiently effective and it stops flowing here. But if you still have supply of lava at the source, lava breaches levees and produces side lobes. In this way, you produce this dendritic system of gentle ridges that are cooling limited flows. And if there are many sources and many flows partly overlapping, you produce so-called compound flow fields, like schematically shown here. And so this is exactly what we see in this part of Mare Imbrium. Then we can see stratigraphic relationships between these and these flows. So we see that this flow is probably the youngest one in this scene. This is older because this is on top of this one. And we see cross-cut relationships here. So this boundary cuts dendritic system of ridges in this compound flow. So this is younger than this. So here we see that this high fusion rate, volume-limited eruptions are later than these lower fusion rate, cooling-limited flows. Another example from Mare Serenitatis. So it is part here. Well, again, we see the boundary between different morphologies of mare-forming flows. Well, this is smooth. We don't see any morphological features here related to emplacement of lavas. And we see some topography here. It's smaller scale. It is lower amplitude. It is like 2 to 3 meters vertical amplitude and about 2 kilometers characteristic horizontal scale of these slopes. And probably it is more or less of the same dendritic pattern of compound flows that we see here. And so this is just smooth. So again, different flows, different mare-forming flows, different volcanic styles. So what is this smooth flow can be? We consider two possibilities. It is possible that it is just one huge lobe of just flooding flow if you have huge effusion rate and just flood the whole surface. It is possible in principle. I'm not claiming this is what is going on. These flows are old. So there is a question, if we produce flow like this and let it stay to the surface for 3.5 billion years, what will happen to it? We know that small features on lunar surface disappear due to regolith gardening. There was recent work by Caleb Fawcett and Brett Thompson. They studied kilometer-sized craters and they calculated characteristic diffusion coefficient that tells us how quickly small-scale features are erased from the surface of the moon due to regolith gardening. They have this characteristic value of diffusivity. If we apply diffusion process of removal of topography to this lava flow, we would figure out that it would survive 3.5 or even 4 billion years on the surface. You need small-scale features to be erased. So if we produce similar dendritic patterns, similar compound flow, but with very small lobes, less than half a kilometer, then it can be erased during lifetime of this Mare surface. So another possibility that this is old compound flow formed by small-scale lobes. So this is what I wanted to tell. My conclusions that we have a method of seeing individual flows that form Mare surfaces. It is the trended topography maps, and we see different morphologies, different kinds of Mare-forming flows. And so this is work in progress. Jim and his students continue working and analyzing of these flows. Thank you.
you. Is this working? So are there any questions? Okay, well, thank you very much. We appreciate your talk. Okay, so next.